it then. So I'm just changing this too. So welcome everyone. Sorry for this confusion, but just like I would like to speak a little bit about the MMIC design of gallium nitride millimeter wave operation. So I think Peter has set the floor excellently for what I'm going to say. So I'm speaking here for as a more to teach on this item rather than showing good results. But I think it's interesting what we have in mind. So so I'm also still doing this in the sense of that we have applied research involved here. So we are also actually doing what we are talking about. So that might help you. So this is good. And the point I'm trying to make here is that this gallium nitride is actually useful to solve a problem we have on this planet, which is effectively is that the data consumption we have per month is actually exponentially exploding, as you see here. So it hits us all. And what we are trying to arrange is we will develop very new systems. So this is one of these examples which we are playing. And the point here is that we have demonstrated 200 gigabit per second point-to-point links, which can actually accommodate the performance of what we will need in the future to do that. The trouble is this is awfully inefficient because physics actually is working against us. We are going to higher frequency to the millimeter wave range, as was explained in various previous talks. And the story we are trying to make is how can this ever be efficient? And when we are looking at the sustainability goals we have all set for this planet to save it from catastrophic use of carbon dioxide and other gases, one thing we clearly have to do is work on three items, and it's important that gallium nitride actually puts out solutions for at least two of them. The first is that we certainly will work on efficiency all the time, but I'd like you also to think in other terms. So for especially the second goal is sufficiency. That so the consumptions of that we are doing have to be lowered, and that is quite true. And second and third, also the consistency that we have to do things in a more friendly way. So, and the reason it has to do with the 200 gigabit per second link, this is good. And it's also can also be even efficient, although the amplifiers will not be efficient, but per bandwidth, actually they are going to be. So this is quite helpful in a way. So this is the goal of this research, which we can show. So I'll go directly to the technology we use. We have various flavors of different technologies of 70, 100, and 150 nanometers of gallium nitride. These are advanced technologies we use. So there you see the gates on the right, and we have rolled them out that we can lease that. I can show power operation here today between 28 and 280 gigahertz based on gallium nitride, which is helpful to especially for the master course here. And I think that's maybe a good solution just to help you on that. So the point I'm trying to make here is that we can show how can we improve the performance. We will work on the gallium nitride MMICs, which have always good drain efficiency and density, and again in comparison to competing technology is probably not as good, but there will be solutions in this talk how to deal with that. And as Peter has already stated, we have the impedance matching, which is changing a little bit with respect to what we do in terms of impedance matching at the higher millimeter wave. It's actually a bit different than what Peter has said. We are working on the combiners heavily, also due to the high power. And then there's various tricks you can play actually to run gallium nitride also into this operation. So let's start with two examples. We have plenty more, but let me give you some flavors of what is interesting in the design. So when you're speaking about a typical 5G or plus signals, for example, at 28 gigahertz, you will still have to deal with a very high peak to average power ratio in an OFDM signal. And what you will want to do is to have either a Doherty or something in a MMIC, which actually will, at the end of the day, will give you decent performances in terms of average efficiency. So the trick here is that we will work on this average efficiency, which is still for anything in the millimeter wave quite painful. So we have worked out the economics for 28 gigahertz, and it's not good. but we have also started to build dualities which can reach up to power added efficiencies in the back of typical dualities of up to 40%. So that's something we can do. When you look at this from a design side, and here I'd like to show you one thing which Peter in a way has said already, but which I would like to add to, that is that when you are going to the real performances of maximum for the respective frequency, you're always ending up in this domain of the Smith chart, which is quite true. There's various reasons. You need more power, you're going into compression, you're going into some back-off situations, and the tricky thing in the design, so it's not interesting just to shoot for this maximum efficiency here in the PAE versus power domain, but you have to find that optimum for a respectable bandwidth, because only then it will be sustainable for a back-off operation. And what I can show in more detail, but I'm not showing today, is that this matching problem is actually getting worse. So it's not only the typical load resistance we have talked about a lot at the lower frequencies, but is to get a passive matching down from this regime back to 50 ohms, and that is exactly what Peter has said, that you typically missing the high Q networks, which then again will limit the bandwidth, and that again will limit the joule per hertz efficiency. So that is one of the key messages from this talk. The second thing is when we are going to high performance GaN amps, due to the gain issues, we have played with some very nice mimics here in the past, and I would like, so we always have less power combining required, but if we go for linear efficiency, we still need a high peak power. So again, we need also a decent average power. So for example, I'd like to show you one example for the higher band. This is something we built for the E band, which is 71 to 86 gigahertz here, and it's quite tricky to do that, because both on the, as was shown for the input and output matching networks, you have to get the right configuration to get the drive right and to still maintain the bandwidth. So what you're seeing here as an example is particularly also the drive levels for a specific output stage. So you have 4 stage, and at the same time also get a low loss power combining to do that right. So these are messages which can help. And when you then look at the performances, you see here small signal wise, you can actually cover the full E band with from 71 to 86 with gallium nitride with a respectable power level, and it is because it's a linearity problem, you will need that peak power, and then you still get decent efficiency also in the peak here, which are going up to, for this power level, I mean, to 18.5%. So it's a good combination of power and efficiency, again, solving the linear efficiency problem. Going a bit to the transistor level optimization, Peter has shown that, so I will speak a little bit more about the power, the RF properties you get here. So when you're going to higher frequency, we'll take some extremes here. What we will do is we just play, for example, with the layout. So one thing you can do is just, as Peter was saying, play with this source gate distance and also play with the gate drain distance. And as you are critically changing also the gate to drain capacitance, you will actually find some very good reactions there. So one way of looking at this is, for example, when you take the various cutoff frequencies and look at the bias dependence, you see here that one value is nothing, many values are useful. So you see actually that the distribution over bias actually is changing. I saw some discussion of the capacitances over bias in the chat. So you see here, this is something you can nicely play with. And then also for the power gain, you see that it's particularly good to drive gallium nitride to higher voltages to reduce the CGD, and then to get decent combinations of the output conductance and the capacitances. So you see here that this is actually first giving you a lot of speed, but also giving you relatively well-behaved characteristics. So that's depending whether you are after linearity or gain, you actually get that result. And here it's, for example, if you take the respective gain at 100 gigs, which is what we are looking at here for this device. So that's you see that you're still getting decent usable gains in the range of something you can design with. So that's helpful. And again, now from a different flavor. So the previous data I showed you for to prove my point. For previous data, I was showing 28 gigahertz, but again, when we are driving these devices to the wild and we are going to G-band, here it's a low pulse simulation for 180 gigahertz. You see actually what's happening. So you see the gain you actually would get for maximum gain is the gain cycles. The blue ones are okay, but the power gains again drive you to this region, which is a bit tricky. So again, when you're going to the extremes, you are bandwidth limited, and also the matching actually will demand its price. So here we made some devices out of that. There's a 4-stage and a 5-stage amplifier which has been used and processed, and you see here that that you actually can reach with still the 4-stage. You can reach about 10 dB of gain. The trick is that it has a 190 at the x-axis, so this was something we were quite proud of. And you see actually it's working well, and this optimization actually can get you decent performances there. And then you also have the 5-stage, which even round gives you just the added gain. So this is quite nice and can help. And then also there's power operation, and you see here that at least there's, I think, indium phosphide is still a very happy contender there, and also silicon germanium can do some nice work, but we are still not so shabby. What you see that clearly is, of course, because we put it to the end, the efficiency is essentially at 0, so it's 2%. And I clearly say that because it was intended to be that way, because we were driving to the wild. On the other hand, when you learn that and learn to deal with that, we essentially going in the right direction, because even if you got to something like 10 or 20% with these devices, then based on the bandwidth you're actually achieving, you're actually quite good. In this efficiency, we are already getting ahead. Then when we are going to the passive networks, there's also some learning here, because we have to integrate. Peter was talking about the Q. I also speak about to get compact networks. So we need to make the parasitics low, because otherwise it will not work nicely. And here with what we created, so there's some, for example, here an AC coupled X junction to get the staging of the transistors. This is just a trick, but you get a very dense design for that. And there were some tricks played, and this was helpful to realize designing those items. And here you see, for example, this is then a 10-stage device, again taking a process to the extremes, but it's quite helpful from a design perspective to learn that. And applying all these items, you can actually drive a process very much to the limit. So that's what you see here. So you can actually get gain at 200 gigahertz. And the surprising thing is that the related bandwidth is also quite good. So you're seeing that this is actually quite wide. And we are seeing, I will show this in a minute, that we are also seeing this performance at lower frequency quite nicely. And you see here the matching is definitely an issue. You see that there's, as anticipated, we are limited by that, but it's some learning about why you're losing the performance. Then also some large signal performance. So the surprise thing is that you can actually squeeze something like 50 milliwatts out of a single transistor at 195 gigahertz. So this is quite promising. So when you take it there, you're actually getting decent performances, and there's not so many performances yet which have demoed the same. So that's quite helpful, and it tells you also something about the potential once you go further ahead. Here's the bandwidth performance also for power and efficiency over bandwidth. So this is something which is quite useful. We can also play some other. You can also then, if you had several advances, and this is also not the newest result, but you see actually here that we can actually increase the power, and by now it's actually more than what we have on the screen here. But when you just calculate on MMIC level the power density, this is promising. So that makes some sense to pursue further on. Coming to another technique, the Cascodes. I mean, this is for D-band, again, similar but it's a different story from a design perspective, which is what I'm talking about today. So when we use Cascodes, we are again reducing further on the feedback and doing something which is already, as Peter was showing, very good. And at the same time, we can also further enhance the gain per Cascode. And the trick, of course, then is that you have to sacrifice some of this achieved gain again to make sure the story is stable, and you have to be quite careful in order to make that happen. But it's possible. So just for sake of demonstration, we did that, and you can actually, when you do the right things, and here's an integrated Cascode on the left, how to play with that, and which can also be stabilized in a way that you're not losing all the additional gain created by the reduced Miller effect again, and sacrifice it for stability. But you see here that the promise of, here it's shown for 2 wafers, is actually quite good. So you see there's plenty of gain available also over the beginning of D-band. And then here you can actually show a good power amplifier based on that. So that was something that was mostly for demonstration of the topic at the time. And you see here that again you get quite a wideband performance in small signal, actually a bit higher than originally anticipated. You could also can get this thing stable, and so it's something which is helpful. And then also some large signal performance. So surprisingly for the D-band, actually the PAE is not as bad as anticipated for a Cascode. So that's something you can definitely use. And you're seeing here that the gain is good, and also the power levels are something you can see most of the time beyond 20 dBm. So that's also something which for this bandwidth again is quite useful. Same for PAE, I wouldn't say optimized, but if you tweak it, you actually get 16%, so that's not too bad, but it's certainly not over bandwidth, but it's something which is at least promising that you can tackle some of the D-band frequencies. And here again, for different biases, you also see the impact there. So this is something which may be of help for demonstrating further, because the D-band is getting maybe the next story after the Ka band. Going ahead, also some more new results. I promised you earlier some wideband performance. So here you see, for example, something we published recently for higher millimeter waves, and this is a wideband design which is quite nice, which is again a design ranging from 80 to 120 gigahertz. So the relative bandwidth is quite nice. And you also the output power is also beyond 23 dBm, and at the same time you see a good matching. And what is also quite good is that the noise figure actually we are getting with these devices is also quite broadbandly good. So I think I like that. So you see there it's in the range of something like below 5, and that was already came in many instances came as a surprise. It's going up. There are different designs which are also better than that. This wasn't necessarily designed for only noise operation, but the combination is quite useful for various applications. So these are nice circuits. The other thing what we also did recently was a comparison, for example, classical mixers. So there's other functions than LNAs and amplifiers needed. And here, for example, this is something we're working on. You do a classical FET mixer and a passive one, and we're comparing these items for also linearity. And this is also quite interesting because the left two designs are 35 and 50 nanometer very classical FET designs. The right one is 100 nanometer. The right is 100 nanometer 100 gallium nitride mixer. And when you take that ahead and you compare the performances, you learn some things. So the first thing is that that the conversion gain in the passive mode actually kind of scales with the metamorphic performance. So you see here for D band, which is quite a high range for millimeter waves, so from 120 to 160, you see that with an LO power of 4 dBm, you get a good conversion gain as expected for a FET, and it's still fully passive. And the for the gallium nitride, when you take similar LO powers, you are a bit worse in the measurement, so you lose a little bit, and then if you drive it, it's actually getting better. So it's quite heavy what you have to do in a low power in order to do that, but you see there's some promise in doing that, so that's quite useful. So it's quite comparable, and we have various other data taken now that justifies also a linearity in this linear operation. And as the upconversion process, when you go to millimeter wave operation, is also a pretty challenging process, which will also require a lot of energy. It's also interesting not only to look at the PA level, but also look at the linearity of the full transceiver chain just to do that, because you have to consider also signal generation and upconversion to build an efficient transceiver. So, and then also something which is just, we are showing from time to time, so this is probably very high for gallium nitride. So this is 265. This is something which you get gain also, at least because I'm speaking millimeter waves, and just to show that we are not starting only at 28, but we can take it to the full range. And this is not the major scope at the moment, but as we have a tradition also to go to the higher domains, there's also work to be done there in the future. So I hope I didn't kill you with all these different circuits. I hope it was interesting, and I hope you're in a better state than this guy on the screen. And if you like, just a summary, the gain is probably still the enabler, as Peter was saying. We can do various tricks to do that, and can also help very much with efficiency. And we have various demonstrations out there, and the full transceiver chain today is the main focus, not just the PAs. The PAs also are getting consistently better at all frequencies, as I was indicating, but it's also contributions on the full transceiver chain. So there are some references here, and if you are interested where I came from, here is the appropriate notes, and I hope you enjoyed my talk, and thank you very much.